Can you see the screen?
Yes, doctor.
All right, so today we're going to proceed with quadratic form and convexity. Okay, so last week we have done with the introduction of optimization. Okay, we have done with what is optimization. There are two types of optimization, unconstrained and constrained, and where can we apply the optimization method. And then the basic theories, local extremizer, global extremizer, by looking at the graph, right? By looking at the graph, by looking at the necessary condition where we have to find the critical point first by differentiating, right? Remember? And then find the local extremum at the certain function. Okay, so now let's proceed with this quadratic form and convexity. Okay, so what is quadratic form? Okay, before we can proceed with higher order of the polynomial form, okay, let's start with the quadratic form and identify their convexity or concavity. Okay, so now what is a quadratic form? So a quadratic form is a function of n variables which can be written as this. So the summation of I and j for aij, xi, yj. Okay, where the aij here are constant. Okay, so this is constant. In matrix vector notation, it becomes x transpose ax. Okay, so we have a function. Okay, let's take a look at the example here. We have a function x1 squared plus x1, x2 plus 3x2 squared. So we can form this function into x transpose ax, where A is n by n symmetric matrix. Okay. So why we need to understand this metric vector notation? Because we can apply to this quadratic form. Okay. So now, what is A? A is n by n symmetric matrix. So we want to represent this function in terms of x transpose A x. So we need to understand what is your A. So given here, your A is 1, 0.5, 0.53. So this represent by x1, x2, x1, x2. Okay, so how can we make sure the matrix of A here can be represented to this function of x1 squared, x1, x2 plus 3x squared. So, and you can understand, your x here is in terms of what? x1 and x2. So x transpose is written by x1, x2. Okay, your A is given by 1, 0.5, 0.53. Why we need to separate this 0.5? Because initially it is 1 here, because we want to have a symmetric matrix. Okay, remember what is symmetric matrix? Anyone? Yes, of course, symmetric matrix is a square matrix. Okay, symmetric matrix is when Aij equals to Ji, right? This is A11, A22, but A12 and A21 both are equal. Okay, so now this is X transpose. This is A, and another one is X. X1, X2. So if you expand this, you can get the function. Okay, so how can you expand this? First, you multiply the last two matrices. Okay, multiply here, you should get what? X1 plus 0.5 x2 and then 0.5x1 plus 3x2. Okay, again, multiply with x1 and x2. So you will have here x1 is x1 squared plus 0.5 x1 x2, x2 x1 plus 0.5 x1 x2, x2 x2 plus 3 x2 squared. So here become 1, right? 0.5, 0.5. So this is how can we represent the function to the matrix, symmetric matrix, and you can prove it again by multiplying all x transpose ax to get the function back. Okay, clear? All right, why don't you try B? Try to expand back. Did you get the function now? This is basic linear algebra, right? So you have learned this. So basically, this is how we can construct the symmetric matrix from the function. We need to understand here first before we proceed with concavity and convexity. Okay, try B. Try to expand. This one is x1, x2, and x3. So you have x1, x2, and x3. Your symmetric form is given A and x1, x2, and x3. So basically, what can you say here? For the diagonal, you just follow the leading coefficient of their variables. So this is 1. Okay, and then there is no x2, x2. There is x3, x3. So 2. So for x1, x2, and x1, x3, you just divide by 2 because we want to have a symmetric. This one is 1, so that's why 0.5, 0.5. This one is 4, that's why it is 2 and 2. Okay? Clear? Understand or not? All right, got it? Got it, guys? Okay. All right, so basically from this example, you can say that this quadratic form can also be written as the summation of xi, xj. So for this one, x1, x2, your A is what? Your Aij here is refer to the what we call here? The value inside the matrix here? Refer to the cell value, right? So this one x1, this one is x2. All right, so this is how we notate the quadratic form in terms of function. So this is in terms of function, where for this example, this is in terms of function, right? A and B. And we can also notate the quadratic form in terms of a matrix vector. So in terms of X transpose AX. Okay, so now you understand this quadratic form can be written in terms of function and also a metric notation. Okay, so A is a symmetric matrix which is obtained by the function given. Okay, so now why you need to understand the quadratic form? Because we want to understand the characteristic of the quadratic form. Okay, so now a quadratic form, okay, XTAX here is called positive definite if it is greater than 0 for all x except x equals to 0. Then, why we need to understand it x positive definite or not? Because we want to identify its convexity. So the function is convex when the the quadratic form is positive definite. When it is positive definite, xt ax greater than 0, then it is positive definite. Then we can say that it is convex. Okay, clear? Understand or not? All right. So that is the first characteristic of convex, where the quadratic form should be in positive definite. Okay, second, the quadratic form is called positive semi-definite if x transpose ax greater or equals to 0 for every x. So maybe the value should be positive and sometimes it can be it can be 0. So when it is xt ax greater and equals to 0, then we call it as a semi-positive definite. Okay, and a quadratic form x transpose ax is called indefinite if xtax greater than 0 for some x and xtax less than 0 for others. Okay, so this xtax here is the quadratic form. Then we can classify to 3 types. It is positive definite, right? Semi-positive definite and indefinite. So what if it is indefinite? Maybe there is a positive value and also there is a negative value. In what? In a matrix A. Okay, later we can discuss how can we identify the value. So this is theoretically based on quadratic form only. Okay. So now we have 3 types of positivity definite. So the first one is positive definite. The second one is semi-definite. Sorry, positive semi-definite, and the third one is indefinite. Right? Okay. So for this case, this is quite hard because we just want to take a look at the function. Okay. So now for the first one, 4x1 squared plus 4x1 squared. Okay. So all values should be positive here because there is square, there is plus there. Then we can conclude that this z is positive definite. Okay. And for this one, x1 and x2 squared, maybe there is 0 value, so we can conclude that it is positive semi definite. Okay, and for this one, it can either be positive or negative value, so we can say that it is indefinite. This is for simple function. But what if we have such a complicated function? It is quite hard, okay? Because we need to understand the function. So later on, we're going to discuss another theorem where we can just identify their positivity definite based on matrix. Okay, so this is given. Why it is positive? Because x1, x2, sorry, because z is positive except x1, x2 equals to 0. Okay, so for the second one, it is semi because z is positive except x1 equals to negative x2. Okay, and then the last one indefinite because sometimes x1 greater than x2 and negative for x1 less than x2. Okay, it depends on the values of x1 and x2 here in order to identify their positivity definite. Is it positive? Is it semi or indefinite? Okay, now let's take a look at this theorem in order to identify the positive definite. Okay, because it's quite hard to just read from the function, right? So theoretically, we can understand this function because this function is quite simple. Okay, so now by using this Sylvester's theorem, right? Okay, by the way, understand or not? Are you following this? All right, good. Okay, so now by looking at this theorem, how can we identify the positivity definite of the quadratic form? Okay, now a quadratic form X transpose AX here is positive definite if all the successive principal minus of the matrix are positive. Okay, remember for positive definite, by looking at the theorem previously, XTAX must greater than 0. For semi-definite, it should be XT X transpose AX greater and equals to 0. Maybe there is a positive value and also a 0 value. And for indefinite, it is a mixture of positive and negative value. So looking at this theory, okay, we need to understand in order to imply to the Sylvester's theorem, where we can say that it is positive definite if and only if all the successive principal minus of the matrix A are positive. So that's why it is important for you to understand how can you construct the matrix A from the given function, right? So you have a function, you identify what is the matrix A, what is a symmetric matrix, okay? And you need to understand the characteristic of the matrix A. Okay, how? By looking at the successive principal minus. Okay, example here. Look at A. A is given by 2, 1, 2, 1, 3, 0, 2, 0, 5. Okay. How can we take a look at the successive leading principle? Okay, so first, let's take a look at A first. Okay, what is the minor of A11? Which is here, right? Okay, and then the successive principal minor for A22. Then it is 2, 1, 1, 3. This one. This is A11. Look at the leading only. Okay, this is A11, this is A22. And then what is the leading successive principle of A33? So everything here. So what is the value of this? What is the value of this? We want to find what? Remember? Anyone? Okay, so now find the values of determinant of each leading successive principal minor here. Okay, find its determinant. If all the values are all positive, then it is positive definite. If all values are in terms of positive and also zero, then it is semi. Then if all the values of determinant are a mixture of positive and negative, then we can call it as indefinite. Okay, try it. What is A? What is B? Understand? Okay, try to do this both. What can you conclude with A and B here? What is your B11, B22, B33? Okay, anyone want to try? Of course, A11 and B11 is 2 here, right? This one is what? What is A22?
5.
A22 is 5, A33,
13.
13. Okay. Then what can you conclude with A, with the matrix A there? A is
Successive exponent.
no. The successive principal minor is given by A11, A22, and A33 here. Then we identify each determinant values there. And if all values are all positive, then refer to the first characteristic here. Then we can say A is positive, definite. Understand or not?
Yes, Doctor.
Right, try B. B11 is 2. What is B22? What is B33? Okay, then
Yes, Doctor.
so B22 is -7 and B33 is
47.
47. Now it is a mixture of positive and negative values. Then we can say B is what?
Not a positive determinant.
This one, indefinite. Okay, remember? So B is indefinite. Why we need to understand this positive, semi, and indefinite? Because we want to make a conclusion in terms of convexity and concavity here. When the function is positive, definite, it is convex, right? Otherwise, it is concave. The function is convex only and only if the matrix or the quadratic form here is positive, definite. Okay, again, first, this is quadratic form in terms of function. And then you know how to convert to a matrix vector. Why we need to have this matrix vector notation? Because we want to identify its matrix, where this matrix A can define their positive, definite, or semi-definite, or indefinite. So how can we identify? Basically, based on the function itself, where you need to understand the function nature, okay? And based on Sylvester's theorem, where you just can take a look at the matrix A, where if and only if all the successive principal minors are all positive, then we can call it as a positive definite, just like A here. Okay, when all successive principal minor here are all positive, then it is positive definite. So refer to this definition. When it is a mixture of a positive value and also zero, okay, then it is semi-definite. If you got zero here, let's say A11 is 0, A22 is 5, A33 is 30. So it is a mixture of a positive values and zero. Then we can call it as a semi-definite. And then the last one, when it is a mixture of positive and negative value, then we can say that the quadratic form or the matrix A is indefinite. Okay, so from here, when it is positive definite, then we can say that it is convex. Otherwise, it is not convex. Okay, clear? All right, try this problem. First, write in terms of a matrix vector notation. Okay, and then is the matrix singular? How can you determine the singularity of a matrix? Check its determinant. If it is equal to 0, is it singular? If it does not equal to 0, is it not singular? You check. And then show that the function is positive definite. How can you show? By looking at the matrix determinant. Then conclude if the function is convex or not. Okay, try. Okay, how can you check the matrix is singular or not?
If the determinant is 0.
Okay, so the matrix is singular when the determinant is 0. Just check the singularity. Okay, anyone want to try? What is the quadratic form in matrix vector notation there? Okay, done. Okay, what is the quadratic form in metric vector notation here? So in terms of quadratic, in terms of matrix vector notation, so you should write in terms of xt, ax. So we have x1, x2 here, then what? What is your x1, x2? What is your a and x here? Okay. So it is x1, x2, x1, x2. We take a look at this one, 1 and 3. And this one is 1 and 1. All right. All of you got this? Okay, so what is it? The matrix singular or not? Check the determinant. Okay, the determinant is equals to 2, which is does not equals to 0. Then it is non-singular. Okay, when the matrix is non-singular, then we can proceed with the next calculation. Why? Because for singular matrix, we cannot do further investigation because singular matrix that doesn't have inverse, right? So it's just that matrix. It is singular. Okay, we cannot proceed with further investigation on that matrix itself. So that's why you need to know, is it singular or not? So when it is singular, then you just cannot proceed with the further investigation. But now we have the value of the matrix, right? Then we can proceed with further investigation. Let's say you want to identify their definiteness and so on. So now show that the function is positive definite. Then by showing its successive principal minor are all positive, right? So we have A equals to 1, 1, 1, 3. Then you just identify what is your A11, A22, because we have only 2 by 2 matrices. Okay, A11 is 1 and A22 is 2. Both value are all positive, then we can say that it is positive definite. Then when it is a positive definite, then we can say that it is convex. Okay, everyone, clear or not? Anyone has question? Okay, good. All right, now let's proceed with the next topic. which I didn't give it the note, right? So let me share with you through WhatsApp group. Later I will attach it on e-learning. Wait. Okay, so we have identified the convexity of a function in a quadratic form. So why we use quadratic form? Because it is for n variables. It's a function of n variables. So now we have several variable functions. Okay. Okay, still we are in the same topic. We want to identify its convexity, but now let's focus on several variables functions. Okay, consider n variable function. Okay, we have a function x of x1, of x2, x3 up until xn. Okay, then the gradient of the function. Okay, we want to understand the gradient of the function is a vector of first derivative of f. Okay, or we can say that this is Gx. Okay. Then the Hessian matrix of f is denoted by big Gx here, which is n by n symmetric matrix with the element of Gij. This is second derivative of fx. Okay. Before this, we have a matrix form of A. Now we have a Hessian matrix. Okay, so for this Hessian matrix, it is for several variables function. So now the necessary and sufficient condition for the critical point of x0 to be extremum if the first derivative of x0 equals to 0 and the Hessian matrix H at x0 is positive definite and negative definite. Okay, when it is a positive, it is minimum point. When it is a negative definite, then it is maximum point. Okay. What is positive definite? All value are positive. What is negative definite? All value are negative. But before this, we have indefinite. We don't know their definiteness. Is it positive or negative? That's why we have a mixture of the values there. Okay. Now, definition. A matrix is a positive definite if the successive principal minor determinants are positive. Okay. And a matrix is a negative, positive definite are positive. A matrix is a negative definite if the kth successive principal minor has a sign of -1 to the power of k. Okay, means that it is alternately changing sign. Okay, let's take a look. The kth minor principal determinant for n by n matrix is defined like this. Okay, consider the function here. Right. We have a function of up until 3 variables, x1 to x3, x2, x3 minus x1 squared minus x2 squared minus x3 squared. So the first necessary condition, first derivative equals to 0. So we need to differentiate one by one, depends on the variable. df del f del x1, del f del x2, del f del x3. Okay, and then equate them all to 0. Okay, then we can find their critical point of x0. So this one, you just need to solve this simultaneously. x1 minus 2, x1 equals to 0. x3 minus 2, x2 equals to 0. 2 plus x2 minus 2x equals to 0. So we have 3 variable, we have 3 equation. solve them simultaneously and you can have the critical point of x naught there. Okay, clear not? Up to this part. So now we want to construct the Hessian matrix. So before this, we just have a matrix, right? It is symmetric matrix, but that is only applicable for up to quadratic form, which is n equals to 2. Okay, now we have this kind of function. It is quite hard for you just to form the symmetric form. That's why we form the Hessian matrix. So how can we form the Hessian matrix from here? So Hessian matrix is formed by looking at the second derivative of f there here. The Hessian matrix is denoted as G, which is n by n symmetric with the element of del squared f over del xi del xj. Okay. We don't have enough time. Okay, this one. So if we have up until x3, x1, x2, x3 here, then the Hessian matrix is given by, okay, we have fx1, x1, fx2, x2, fx3, x3. So you differentiate f with respect to x1 with respect to x1. Okay, this one is fx1, x2, fx1, x3. Okay, depends on your given function. x2, x1, x2, sorry. F, x2, x3. F, x3, x1, fx3, x2. Okay, so now you have your fx1. This is fx1, right? So you just need to differentiate again with respect to this, referring to this x1, 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 x2, and so on. Okay, so now let's do this. All right, so we have fx1, fx2, fx3. So in order to get fx1, x1, so you differentiate this again with respect to x1. That's why you have minus, where is the matrix? Fx1, x1, minus 2, yes. Okay, so minus 2. And then the second part is fx1, x2. So you differentiate what? You differentiate fx2 with respect to x1. So there is no x1 here. That's why it is 0. Can you do this? Can you try this? Try to form the Hessian matrix first. You know how to do it or not? Or else we just proceed with in our next class. You can try it first. Can you? Anyone has question? So I believe all of you understand. Okay, so as for today's activity, try to construct the Hessian matrix. Okay, first try to construct the Hessian matrix referring to this. Okay, or this. And then identify its definiteness by looking at the definition of this. A matrix is a positive definite if the successive principal minor determinants are positive. Okay, same with the previous one, and it is negative definite if the kth successive principal minor determinant alternately change the sign. Okay, so when it is positive definite, when it is positive definite, then the critical point, the extremizer are maximum. When it is negative definite, sorry, this is minimum. Then the extremizer are all maximum. So that's why it is important for you to understand the definiteness of the Hessian matrix, and also the previous one is the symmetric matrix. Okay? Okay, try it. Try to understand the Hessian matrix and prove whether it is negative definite or not, and then you can conclude the critical point. Okay? Anyone has question before we stop? So from 1 to 10, where are you for today's lesson? Okay, good. Alhamdulillah. Okay, by the way, I'm sorry for the late note. Okay, because I have the notes with me, but most of them are in Malay. So I need to simplify it first before I give it to you. Okay, so please consider the letter notes I give it to you. Okay. All right. So I stop sharing. Wait. I need to share with the attendance. Okay. Sekejap. By the way, does this class have